All right, so this video is sort of long overdue because we're supposed to do it yesterday when the contest was over. But here are solutions to A through C for educational code forces round 173, and I'll probably try up solving D um, and make a video on that. I've been a little bit like, when I have been productive, I've been doing like college applications, so not really too much code forces because college applications are really really annoying, especially when you're applying to a decent amount of schools. But yeah, let's just get into this. So problem A was a fairly simple question. So the idea is that like you have a coin with some value and you can basically split it into two coins as long as the value is greater than 3. And the idea be and basically like as long I basically want to say like how many coins can you get from this. So I think this is like fairly simple. It's just pretty much you want to see how many like fours you can fit in this number, like how much times you can just like divide it by 4, as long as it's greater than 3, and then that's like, and then 2 to that number, like 2 to the count, will be your answer because it's basically just like a binary tree. So I sort of this was when I was recording and I had to pick a new recording, so that was from the last one. But yeah, it's like a binary tree, and so it's something like this, right? So it's basically just like not yeah, basically it's just um like how many love like you need to count the amount of like levels that you have and then do 2 to the amount of levels, right? Like I just think it's a pretty simple question. Like there's really not much going on here. Like just looking at the code, probably already have an idea of what the solution is. So not pretty interesting. I don't know why is that board just loading. It's a little annoying. Okay. So problem A, I didn't particularly like problem A. If you're wondering why I'm a grandmaster, I'm not. It's just because like during Christmas you can like change your color. So I like red. And my new user is exothermic, so red is pretty fitting. So basically like this question, you have a digit D and you're writing it n factorial times, and you want to see which odd digits from 1 to 9 divide this number. So I didn't really like this question just because like I had a solution. I'm pretty sure everyone did had a solution to deal with 1, 3, 5, and 9. Like that's pretty obvious. For example, obviously any number is divisible by 1. And for 3 and 9, if you have any like math experience, I guess, you'll know that like a number is divisible by 3 as long as the sum of the digits is divisible by 3. And same thing for 9. As long as the sum of the digits is divisible by 9, then the number is divisible by 9. And it's a simple modulo trick. And it's just um, the reason why this is true is because um, 10 mod 3 is 1 and 10 mod 9 is also 1. So when you're writing like the number out, like every number can be written as like 10 to some power and then times like the digit, and you can like sort of just like depending on what the digit is, like for example the number 56 can be written as 5 times 10 plus to the 1 times 5 times to the 0. So for like mod 3 and mod 9 you can replace all these with 1. So basically it's just you're adding to some of the digits, so that's why it works. But I really don't want to get into math here, it's just pretty obvious to me. So for example, like if you had like n fact well it's not if you had like n factorial times d, like that's basically just like the number of digits times d is your sum of the digits. And so basically it's just saying like like take this, like if you want to know that if 9 divides this, um then you need to know if there's exactly 2 3s in this number or in the prime factorization of n factorial times d. So check if there is you know check if either d or n factorial have a 9 in it, or check if both of them have at least 1 3 in them. and that is how you can check if it's divisible by 9. To check if it's divisible by 3, just check if d or n is divisible by 3. And that's pretty much it. And then for 5, it's basically just checking if the last number is 0 or 5. So yeah, those were pretty easy. The very weird one was 7, and I had to sort of like, I don't know if they have like, let me check their solution for 7. Yeah, I didn't really like this problem. This was like the trickiest case. And again, like unless like you're interested in the math of it, which I'm particularly not too interested in that, it's more so weird. The way I guessed it was like um well, I was sort of like, well, this number here is like d times like 1 1 1 1 1 1, right? A series of ones. And I was just checking like um so if d is 7 is a multiple of 7, then obviously this is divisible by 7. But if this series of ones, how do you know if this series of ones is divisible by 7? So I sort of just like generated like um patterns, or I sort of like just started looking at numbers in the form of like a bunch of ones and seeing which ones were divisible by 7. And I concluded that like um if you have like for example, numbers like if you have a multiple, so if you have like, so for example, say like this is like, say let x be like the number of ones you have in that number of just ones. I'm looking at like, is 1111 divisible by 7, right, or whatever. I'm looking at that type of stuff. Basically, let x be the number of ones. If x is a multiple of 6, like apparently, like it's always like that number is always gonna be divisible by 7. And you can realize that like for n greater than or equal to 3, obviously n factorial is always going to be a multiple of 6 if n is greater than or equal to 3. And so then like pretty much any n that's greater than or equal to 3 will be divisible by 7. And then obviously for d, you can just check if it's divisible by 7 pretty easily, because d is like pretty small, so just do d mod 7. So that's pretty much it. um I didn't, yeah, I really didn't like this question. Because I sort of just had to, I don't know if there, maybe you could sort of just like, my friend had like an intuition on saying like check like the smallest n in which this word, like I don't know, I'm not a big fan of this question at all. If there's a better way to do this, I don't know, but I'm not a big fan of it. um but I used a strategy of sort of just like um seeing patterns, right? And letting those patterns guide me, because that's sort of like this type of stuff. Yeah, I didn't entirely enjoy this, but to be fair, you can just sort of just play around with it and notice patterns, and then hopefully they work. Proof by AC. I obviously don't know why. I mean, I'm pretty sure that knowing the divisibility rule of 7 isn't standard at all, so I don't really. And I think like proving it isn't really worth anything. Like if you want to get better at competitive programming, I think knowing the divisibility rule of 7 would do anything. But yeah, I particularly don't like this question. It wasn't too much of a hassle in the contest, but I just didn't like it. So this question, problem C, um, I thought was a good question. Although I'm a little bit annoyed because I actually like when I read the problem, I instantly knew what to do, but I forgot to like think solve the entire problem. But like I got 80% of the solution like right after reading it, because it's a very standard question, and or uses very standard techniques. So for problem C, yeah, you basically have an array that's -1 or one except for one element, at most one element, and the idea is that like you want to see like all the possible subarray sums. So it's pretty standard that like if you have if you have an array of like elements of one and -1, basically you can achieve any subarray sum in between the smallest possible subarray sum and the biggest possible subarray sum. And the reason for this is because like um the prefix sums of this are is obviously continuous. So if the prefix sums are obviously continuous, then you can think of like just the minimum guy here, or like it just continues every continuous function has some like min and maximum, and basically if you can achieve like so I'm because okay so the let me explain this like much better. And this is the statement I'm trying to prove for like for arrays with only -1 and 1 as elements. Any subarray sum is possible between the min subarray sum and the max subarray sum. So what should be very obvious to prove this is the prefix sums of this array is always going to be continuous. It's always going to be continu. It's continuous along the integers, as in like and by continuous I mean like continuous in respect to integers, not like real numbers. Obviously, 1 to 2. So that's what I mean, right? So it's always like continuous, right? So basically, if you can achieve, so basically, you know that like from the min prefix sum and the max prefix sum, you can achieve any prefix sum that you want, right? This is like the intermediate value theorem, actually. Uh, I have a video on this actually on my channel. It's like intermediate value theorem for programming. So I've seen this many times. Um, but you basically can achieve the min prefix sum and the max prefix sum. And so if you can achieve any, so then that means that like what you can do is like, well, if you want to sort of like so intuitively, if you can do this, you can then this statement should be sort of obvious, because a subarray sum is just a difference of prefix sums, and if all those integers are available for you, like the max subarray sum is like like for example um to me like to me this is like very very or like if you think of like a subarray sum, it's sort of like just a difference of like I'm trying to prove it. It's been a So let's see. You can like achieve any like because this is like the proof, right? Do they prove this? I'm not sure if they do. Did I? But honestly, like because you can achieve any prefix sum between the minimum and maximum, and a subarray sum is just a difference of prefix sums, then it's like, for example, let's say I have available to me the prefix sums 1 to 10. Like I can achieve like the maximum would be 9 because it's just a difference of prefix sums, and the minimum would be like the minimum would be either -1. Well, in this case, like of -1s and ones, it's either gonna be like or not even that, but the minimum would be 1. The idea is that like you can achieve anything, you know? Like the idea is that like if maximum prefix sum is possible, let's say for example, let's just say you have your maximum prefix sum, like it's very easy to like I'm trying to make the it's like you have all these integers available to you. It should be very obvious that you can achieve like if the prefix sum array graph is continuous, then to me it makes sense that the subarray sum graph, like all the possible subarray sums you can make, is also continuous in the sense of integers. Um, but that just seems that's really intuitive to me. So, but I'm not sure if that would be intuitive to someone who just saw this for the first time. You can definitely agree to me that the prefix sum graph is continuous, but the subarray sum graph be continuous? Also, if you all already know this, definitely skip over my explanation um of this. But yeah, I'm just gonna say that the subarray graph is also continuous because the prefix sum graph is continuous, because it's just like you can achieve any of these, and like a subarray sum graph is a function. It's a function of this prefix sum graph. So like if this prefix sum graph, if this function is already continuous, and I'm just taking like a function of that, it's intuitively also continuous as well. So I I don't I can't, like, I didn't rigorously prove it, but it should be somewhat intuitive. But anyways, this is a very important idea you should know in competitive programming. Um but I'm not no like mathematician, so I won't do a formal proof, but this is some idea you should know. And this sort of solves you like probably 80% of the problem, because um, basically wherever this element x is, you can sort of think of it as two arrays next to one on the left and one on the right. And the idea is that like you can sort of just find the minimum subarray sum here and the maximum subarray sum here, minimum subarray sum here and maximum subarray sum here. So like these are the min guys and these are the max guys. And then basically you can iterate through these and just add them to a set, and that's how you can generate some subarray sums that are possible already. But these are basically subarrays that don't include x. So there are two types of subarrays that you should think of in this problem. You should think of subarrays that include x and subarrays that don't include x, right? If you think of subarrays that don't include x, then it's a very obvious problem. It's a very generic, like very standard problem. You just have to find the minimum subarray sum and the maximum subarray sum, and the minimum subarray sum and the maximum subarray sum. That's literally already like that's pretty standard. You can find the solution to that online. It's basically, so this question is just like really easy. But the case that I actually didn't I messed up on, which is pretty sad, is the um, case where you actually have pretty sad relative to the fact that it's not like, if you got this far, it's not really hard to like modify. But if you have like this element x in your subarray sum, that's also a case. So the idea is that like um, a subarray that includes x is basically a combination of a suffix in this array. So let's say this is like a subarray sum, right? Notice how um, for this array it's like a suffix. So I'm gonna write s for suffix, and then it's a prefix. So it's basically a suffix of the left array plus a prefix of the right array plus x. That's basically this combination. So um, the idea is that like um, from here we can say, well, what are all the possible suffixes that I can have, right? Because I'm trying to find like a range of values probably for subarray sums that include x. And the idea is that like what are all, let's say like this is like some range, like from the left side it's like L1 to R1. This is like a range of all the possible suffixes that I have. And for this one it would be like L2 to R2, a range of all the possible prefixes I have. The idea is that like, and then I have to like add x. So the idea is that like um the minimum value that's possible is just L1 plus L2 plus X. But like, the idea is that like, or the idea is that like, okay, so if I have, or the question is, I'm gonna have two ranges, right? Two continuous ranges, L1 R1, L2 R2. These are like, I guess I should do L sub S, but let me actually do this, right? So I have two ranges, L sub S, so for the suffixes, and um, and LP and and RP. And the idea here is that like I want to like combine these two ranges to create a new range. So here's that like I can achieve every value from LS to R because I basically want to create a new range. So I'm gonna like do what's this plus LP RP. What is that equal to? So it's like I can achieve all the values from LS to RS and LP to RP. Now what's the new values that I can achieve? Like um well I can definitely the idea is that like you're gonna have to add these ranges together because that's what it is. You're gonna add, and this range includes like it's easy. You can achieve like a suffix sum of 0 in the left array and a prefix sum of 0 in the first array, so that range includes that. Basically want to see like, okay, what are the new values if I have to take one value from the suffix range and one value from the prefix range. I want to see like what are all my possible values. So it's like I can add it makes this is basically it. um that is just adding them. This is just like obvious. Like it's just like, okay, the reason why you can view this literally like, let's just say you have some range like L, like it's just like it's straight up just adding them, because like the minimum value you can achieve is this and the maximum value you can achieve is this, and obviously you can achieve any value in between that. For example, if I want to like add 1, I could just do ls and then do um LP plus 1. Like it's just very obvious that this is the range, that the new range. And then obviously you have to shift these by x because these subarrays will have x to them, and that's all it is. And that's basically it. You just iterate through this new range, add all those values to the set, and you're done. So yeah, I sort of, but coding this was a little bit annoying. So here is a generic code to find the minimum subarray sum of an array and maximum subarray sum of an array. I'm not going to include it. It's basically Condain's algorithm. And Condain's algorithm, I won't really explain it just because I'm actually kind of tired right now. And you can probably just search it up. It's pretty standard. It's just like if the sum, like, just, yeah, I'm not explaining it. But yeah, it's basically, implementation might not be the best. Make sure you add the empty subarray, like 0 is the empty subarray. And then I'm going to find where the index is, x index is. And you know, there's some edge cases here. Like either you might not have an element that's different than -1 or 1. So just find the minimum and maximum subarray sums and then add everything. Um, you might have something that's in the something that's in the front, so you only have one array instead of the two arrays that I showed. So same thing here, and this time you can just like, if the element x is in the front, then just like go through all the possible prefixes of that array, so in the temp array, and then just add x, this element x, a sub index is x, and that covers the case where subarray sums include x. And then this is basically just an implementation of what we just talked about here, finding the minimum prefix sum and the maximum prefix sum, um, or suffix sum technically for this one, and then minimum prefix sum and maximum prefix sum, and then just like having this new range here. And yeah, that's pretty much it. And then this is the case where you don't include x, and it's a pretty easy case. And then you just print it out. So yeah, this is low-key not a hard question, but unfortunately I trolled it, but I don't think it's hard at all. Yeah. So that's pretty much it. Yeah.